Okay, thank you very much. And I think it's a great honor to be here. And of course, I want to thank the organizers for everything. And of course, I also want to thank Menachem, for all his support and for all his hospitality. I was also looking for a picture of Menachem, but the only thing I found was a picture of Albert Einstein. Well, my wife took it. So happy birthday, Menachem. This is my only slide. I'm sorry, say it again? So the languages are the languages spoken in my home and in Menachem. So that's supposed to be Hebrew, isn't that correct? Yeah. You said the language is spoken in your homes. No, I was saying in my home and in your home. Okay, good. So now. Oh, I see. And good. Okay. Is this all the? Wait, sorry.
There was another one.
This one? Yeah, okay, good. Okay, so what? Oh. So what I want to talk about is part of the program, I guess, initiated by Hampkins studying set theoretic geology. What it is about is that it turned to be interesting to look at which grounds a given model of set theory can have. So a ground is a ground model. So just by definition, you say if M is, let's say, a transitive model of set theory or an inner model or something, let me just write a model of set theory. Then W is being contained in M is a ground if there is some poset P, which is an element of W, and there is a G in M, which is P generic over W, such that M is the generic extension by G. Okay. So examples. What if M is the constructible universe? Then there are no non-trivial grounds, so then everything is trivial. There is a lot of work. A lot of work has been done on more general models. I don't want to talk about kind of general M's. I want to restrict the class of the models which I'm to consider, and you might not be very surprised that I will consider fine structural models. So if you relax this hypothesis a little bit, and if we say that if M is a fine structural inner model, I mean a sort of classical extender model with no inner model with a wooden cardinal, and whenever I write this, I will be a bit, I will be not very precise about iterability. So for most of the times, I will mean that we assume some kind of iterability here. Then there is no. Oh, I did it. Sorry? Then W is no, W is the ground. I mean, in this.
No, but in W.
Yes?
What is W?
There is no W yet. I'm about to tell you that there is no non-trivial W. Let's just look at such an M, and now the statement is there is no non-trivial ground. There is no, every W is equal to M, okay? Okay, so there is another helpful concept in this area. They call it the mantle. So the mantle is the intersection of all grounds, given M as over there. The ground, the mantle of M is the intersection of all grounds. And what we discussed here means that the mantle is also just the model itself. So nothing non-trivial is happening here. So the first L of E model where something non-trivial happens, and I want to discuss this a little bit because this illustrates what will happen later on, even though this is really part of the folklore. So let's look at a third example, namely the least iterable model with one Woodin cardinal. And there it turns out that you have tons of non-trivial grounds. How come? I mean, this is by no means my theorem. This is just a consequence of the extender algebra, so of Woodin's extender algebra. So what you do is you look at M1. So it looks like this. It has a Woodin cardinal. It is of the form L of E. E is an extender sequence witnessing that delta is a Woodin cardinal. And you can think of E as being basically a subset of delta. Okay, so the universe you live in, M1, is of the form L of a set. Okay, and it has an inner model, it has a Woodin cardinal. So how do you get non-trivial grounds? Well, for instance, look at the least measurable cardinal of the model. Iterate the measurable cardinal your favorite number of times. So you get an iterate. You can do that certainly inside M1. It's a linear iterate by the least measure and its images. And now you can start using the extender algebra at the image of delta wherever it is. So the extender algebra, I assume that people kind of have seen it. So the extender algebra is a poset in M1, which you can use to make things generic. So you look at the extender algebra at delta star given by the extender sequence of M star, and you start making this set generic. Okay, so what will happen is that you will create a normal iteration tree. And you can show that inside M1 is sufficiently iterable so that you can at least start out with this iteration. What might happen is that at the very end, you don't see the last branch, but you will definitely see the last model. And in any event, you will get what's called a common part model. So this iteration will produce a common part model, M of t. It could actually, okay, so that if you put L on top, the supremum of the indices of the extenders which have been used is a Woodin cardinal in this model. This supremum is usually called delta of t. So how exactly do you perform the iteration? I mean, the extender algebra comes with a set of axioms corresponding to the extenders, and whenever you find an extender in your current model which violates one of the axioms, you just hit the extender to get rid of that problem. And if you arrive at that model, you will have removed away all these problems, so all the extenders of that sequence will satisfy all the relevant axioms, and therefore you will have achieved that the original model E, that the set E is generic over this model. So for the extender algebra at this cardinal. I mean, it could also be that you actually see the branch, that this is an actual iterate, but okay, good. So what did this show? I mean, we said that we can, you can iterate the least measurable cardinal your favorite number of times. So what does it mean? If you now look at the mantle, okay? So I gave you an example of a ground. So this just shows that if you take the least measurable cardinal of M1 and you iterate it out of the universe, then you get something.
Actually, the branch can never be in the model.
Okay, yeah, I know, yeah. Yes, that's true. Well, unless it's the identity, unless nothing happens, unless you didn't do anything here. Yes, that's true. So what this showed is that the mantle is contained in the model which you get by iterating the least measure on kappa 0, or the least measure of M1, which sits on kappa 0 out of the universe. Okay, I mean, this model looks a little bit like, I think the term core model comes from the Dodge-Jensen core model is the result of iterating the measurable out of L of U out of the universe. So this is a little bit like a version of the core model in that sense, right? So you take the least measure, or the measure on the least measurable cardinal, and you iterate it out of the universe. And this is, so the mantle of M1 is contained in the following model. Let's just write W to irritate Modi even more. So what is W? W you can think of as the result of iterating the least measure of M1 and its images out of the universe and cutting off at the ordinals. Okay. Well, so what I'm doing is I take the least measure, I iterate it and its images, ordinals many times, then I get a model which is kind of taller than the ordinals, and then I cut it off. Okay. So what is this model? This model doesn't have any measurable cardinals. So this is what's called a lower part model, right? I mean, consistency-wise, it has lots of measurable cardinals and much more, but it does not have a measurable cardinal. It's a lower part model. Okay, and you can actually prove that you have equality here. Sorry?
How did you make E generic? You said something.
Okay. The Woodian cardinals are extremely mysterious, yes. They will, by the end of my talk, you will see that they are completely, even more mysterious than you ever thought. I don't know. It's the extender algebra. I mean, there is this algebra. So you write down the set of axioms, and if you have let me not be too precise, right? If you have a set which satisfies all the axioms, then you just show that it's generic over the model. So what's going on in this tree is you look at you are at the current stage of the iteration, you check if every extender satisfies all the relevant axioms, and if not, you take the least extender which violates an axiom corresponding to that extender. So then that problem is gone. Okay, and then there is an argument that this process has to terminate, which I didn't give at all. Okay, so there is, for sure, there is an argument.
What's the relation between the W and the L of U of T?
There is no W on this board. Sorry, where do you see a W? This is an M.
Is that a W?
This letter?
No, L, T.
No, this is one, this is a ground. This is a ground, okay? So this is one of these W's, okay? Now here, I mean, this notation is unfortunate. Okay, let me write, okay, just for ad hoc. Okay, okay, so this argument is supposed to prove that the mantle is contained in this model. Okay, and in fact, you can prove that that these two models are equal. So the mantle of M1 is equal to this model. So the key thing here is not very difficult. I mean, the key thing here is if you assume that you have an inner model, that you have a ground, okay? I mean, you can force to get M1. So the first thing you do is you prove, which is also folklore, I guess, I don't know, that set forcing cannot add an inner model with a Woodin cardinal. So your ground will have an inner model with a Woodin cardinal, and this is your starting point to verify that they are actually equal, okay? Well, you will not, I mean, you do the entire thing inside M1, so you will not hope to get any iterable inner model with a Woodin cardinal, only kind of sufficiently iterable with respect to what you would call short trees here. Okay. Okay, so this settles the thing for M1, and then of course you want to look at more general models. So in a paper with Gunther Fuchs, what we did is this actually generalizes to the situation when the universe is constructible from a set and there is an inner model with a Woodin cardinal. Okay, then kind of this will always be the picture. You take this. You have to identify a least inner model with a Woodin cardinal. I mean, it may be that there is no iterable inner model, that there is no inner model with a Woodin cardinal which is iterable, but still you can make sense of what it means to be the least such model. And if you take the least such model and you perform this thing, you will get the mantle. Okay, so this, even for non-fine structural models, this gives kind of an analysis of what the mantles are of models which are constructible from a set, even if they are not fine structural. Okay, so the next target is what about, if you go back to L of E models, what about L of E's, where E is kind of a proper class? Right. This means that the external sequence doesn't stop anywhere. I mean, it's not the case that from some point on it's just L on top of something. Okay, so, and I still, again, consider L of E's. So it, let me see, I wanted to, I wanted to also sketch very, very briefly, just as a sketch, because this will introduce a relevant method. So I think this is a theorem of Hughes, that if you, again, let me not state it too precisely. So if L of E has a Woodin cardinal, it's not so much surprising by now if L of E has a Woodin cardinal, then it has non-trivial grounds. Okay, how do you prove? One way to prove such a thing is the following. So you look at L of E. Let's look at the least Woodin cardinal of L of E. There could be more than one. Okay. Now do what's called an L of E construction inside L of E. So this would be, for instance, the Mitchell-Steele L of E construction, where you relax the smallness hypothesis. as I said, I don't want to talk too much about iterability. You're making an iterability assumption concerning your background universe, which I don't spell out here. So you're doing an L of E construction inside your model. So you're building a sequence. John mentioned these sequences yesterday in his talk. The point is that if you do an L of E construction inside your L of E and you do it up to delta 0, the extender sequence you construct is not the same as the original extender sequence of E, so it will be kind of thinner. You will, for instance, to add the least measure, you wait for quite a while until you actually add it. You pass the first measurable cardinal of L of E. Okay, so you construct this model up to delta 0, and as a matter of fact, by how things work and how the L of E constructions work and by how the extender algebra looks like, you can just verify that the extender sequence E cut off at delta 0 will be generic over your L of E, which is built inside here up to delta 0. Okay? Okay. And then you just want to, kind of put something on top so that so that when you put it on top, then this thing will become a ground. So how do you do it? Due to the fact that this thing, okay, this is an awkward notation now. So I'm doing L of E inside L of E, and I cut it off at delta 0.
You said it's different, so you put the prime on the...
Yes, yeah. Let's do a bar here or something. Okay, so E up to delta 0 is generic over this model. And due to this fact, what you can do is, you could put L on top, which is not very exciting. But what you can do is you can start putting L on top, and whenever you see an extender over here in your L of E, the model, there is a recursion going on or an induction. The model you built so far will still have the property that this will be generic for the extender algebra. So what you can do is you can take this extender and just take its restriction and put it on your sequence which you are constructing. So what you are doing is you are doing what's called a P construction. Other people call it S construction. The letter P stands for John Steele. So this is something Steele designed. So you end up extending this model by some P, which will have the property, so I cannot give you any details, it will have the property that the original model L of E will be generic over P for the extender algebra at delta 0 of that model. So you found the ground. Yes?
The extender algebra to delta 0 is less than delta 0 CC?
Yes, yes. Mm-hmm. Mm-hmm.
So you couldn't just use the standard trick to build the ground, say, using the approximation property?
I don't know what the standard trick is.
Well, this is that you define the ground using the fact that...
I want a fine structural ground for some reason or other. But anyway, I don't know. I don't know how you...
You have to do something. You can't use the approximation problem because you're going to have the approximation problem. You need the approximation problem because if you have a set out with a small subset and then a model, then exception. You have to build a model relative to which you have your model.
Now at delta 0 you start building, throwing into the model or at bit.
Why don't you guys talk about it later? Okay, I want to point out that here it didn't become really transparent, but it was important. Why did we pick the least Woodin cardinal? Well, the idea, it was kind of necessary to not pick an arbitrary Woodin cardinal, because imagine this delta 0 were overlapped by an extender in L of E, then this P construction wouldn't work. So what would happen is you could do a P construction, but it would give a P so that the alter power of L of E by this overlapping extender would be generic, and this is not what you want. You want that the real model is generic. Okay, and this looks a little bit like a technical problem, but actually it has the fact that you cannot do a P construction if there is an overlapping extender around dramatically, introduces a, how would you say, threshold. And we will come to that in a second. So in a joint paper with Gunter Fuchs, we basically analyzed the situation of when you have an L of E model and you have arbitrary many points which are not overlapped in a bad sense. In other words, arbitrarily large cut points. In other words, if your model doesn't have a strong cardinal. Okay. So if you have an M which is an L of E, and we also assume that it is tame, so there are no extenders overlapping Woodin cardinals consistency-wise in the model, with no strong cardinal, again, you can do kind of the same thing as we did with M1 in the beginning and then with L of a set later on. You can kind of do a more elaborate analysis here. You will get a lot of grounds by, I guess there is an additional hypothesis missing. I want to say that in some sense this model has a Woodin cardinal. Assume also that M has some kind of inner model with a Woodin cardinal in a way which will give rise to interesting grounds. So you can spell that out in different ways. You can kind of say that M does not know how to iterate itself. I mean, if you want to be more precise, you would have to talk about the attempt to, you are in M, you attempt to iterate yourself, inside yourself. So there is a procedure which is described in a paper I have with John, which is called the self-iterability of L of E. So it uses these P constructions, which you saw over there. So they give you kind of a recipe how to try to iterate such a model inside itself. And what we assume here is that this procedure doesn't work. So what in this paper was kind of a bad option is here a good option, because if you have a failure of iterability in this sense, you will get a ground and you're looking for non-trivial grounds. Okay. Okay, then the mantle, how should I write it, of M is contained in a model as on this board. Okay, let me be not more precise, because the point of my talk is what happens in the presence of a strong cardinal.
Why don't you assume there's a proper class of Woodins and then it is M? Because you can just run that construction at any point and P.
Yes, I mean, we also analyze what happens under which circumstances you can prove equality here, and we say something in the paper. I mean, in fact, this is the most difficult part of the paper, to identify hypotheses under which you have equality here. Yes, yes. So let me not say more about that at this point. Okay, so we kind of have a picture. Okay, there was this. I'm not sure about how to remove the tameness hypothesis. So there is work to be done. But now there is an interesting question, namely, what happens in the presence of a strong cardinal? And of course, we still want to keep the Woodin cardinals. So let's look at the least model, which the techniques so far don't have anything to say about. So let me say, let's see. So let M, I don't know, this is just an ad hoc notation. I should say that what I'm going to talk about now is part of a joint paper with Grigor Sargsyan, and this is ongoing research. So currently we call the model like this. I think the order is kind of in Hebrew because this is the least model which has a strong cardinal above a Woodin cardinal. Okay. Okay, so how does the model look like? You have a Woodin cardinal, delta, and you have a strong cardinal kappa sitting here. So this guy is strong all the way up to the top. So it's not very big consistency-wise, right? Okay, so if you try to, you can run arguments we saw before to get non-trivial grounds. I mean, we saw such arguments. And in fact, by the arguments which I gave, you get the following, that you can take the least measurable cardinal of that model, you can iterate it any number of times less than kappa, and you will then get, by this extender algebra plus p-construction ideas, you will get a ground which agrees with that resulting model up to that point. So just to repeat, so you can iterate kappa 0 alpha many times for any alpha less than kappa. Look at the resulting model. The resulting model up to the image of the measurable cardinal will be a rank initial segment of a ground of that model. Okay? So why? It's exactly the same argument before. The reason is that up to here you don't have any strong cardinals. So there are many of these cut points. There are many of these points where this kind of argument works, where you put in a p on top of, well, in this case, some m of t, some common part model. Okay, so this gives some partial information, and then it was kind of a mystery for a long while. What should happen? Do we have more grounds? Are these all the grounds? There was the question, what happens? I mean, you have so you have a class, kind of directed class of kappa many grounds. The question was, is there a lower bound? And there were some conjectures around. And then it happened that Usuba proved a very nice theorem, namely that the grounds of an inner model of set theory are always set-directed. And therefore, this gave a little bit of information about this model, namely you have these kappa many grounds, so there must be a lower bound. What is it? Okay. Simultaneously, Martin Seemann and Grigor Sargsyan worked on this model, and they identified the core model of this model. So this model has a core model. So there is a theorem . So what does this statement mean? This statement means that this model has a fine structural inner model of which this model knows that it is fully iterable, and you have recovering and you have forcing absoluteness. Okay, let's take this as a definition. Okay, so the way they get this is that, so what they do is they start out with this model, and they take this model as the base model of a certain directed system. Actually, the directed system you can think of as basically the grounds you identify by the method we discussed over there. So this gives you a directed system, and you just take the direct limit of that system. Okay, so you get a model which you may call M infinity. It's a directed limit of a system generated by this model, and you use the strong cardinal to prove that inside this model is fully iterable. You prove recovering, and then you can go for the core model. Okay. Okay, and then I visited Grigor in Warsaw This is where the title of my talk comes from. Let me just check. Yeah. Okay. Okay, so so we fix our model, the least extender model, with a strong cardinal above a wooden cardinal. Okay, so the first thing is, so this was really inspired. In the end, we didn't have to use the result of Usuba because we kind of, well, we get a real analysis of what exactly the mantle is, okay? But what we did have to use is something which Usuba had used, namely an old theorem of Bukovsky's. And part of what I'm doing here is it's kind of an advertisement of this theorem. So if you don't know it, it's an interesting theorem. It gives a very nice characterization of when something is a ground of something other. Okay. In terms of, you don't talk about forcing at all. I will say a little bit about this in a second. Okay, so the way they had done this is that, I should have introduced the name. So they define a direct limit system based on the very ground model It's something which some of you are familiar with from the context of analyzing the hordes of determinacy models. So it's kind of a very, very similar thing is going on here. So let's call M infinity the direct limit. I mean, you can define the direct limit in V, but the definition you write down in V is not the one you can write down in this model. So there is a little bit of work of showing that there is something like that you can cover this direct limit by some system inside this model, and so on. Okay, so anyway, I mean, this direct limit, as a matter of fact, will be an element of the model. So the first thing we realized is that it's not exactly M infinity, which will be a ground, but as you are familiar with from the hot analysis, you have to add a little bit, so you make it a hybrid model. I don't know, this is just the notation I use at this point. Is a ground. So this is the direct limit model. So what you do is you construct from the extender sequence of the direct limit model together with one function. What is this function? So you can think of this map as being the map. Okay, so in V, this will be an iterate of MSW. Okay, so it looks exactly the same as this model. It has a strong cardinal above a wooden cardinal. So you can go into this model and form M infinity inside this model again. Okay, and then in V you will see that there is a map from M infinity into the M infinity of M infinity, and this is this map. Okay. Is the map which sends M infinity, and you just restrict it to the ordinals, that's all you need, right? I mean, you live in M infinity, and you run the definition of M infinity, not the one you do in V, but the one you do in your inner model. You run it inside this model, so you get a new M infinity, and this is the map from here to here.
Is this just putting in the iteration strategy?
Sure. Yes. Yes, you can, there is a different way to think of this, namely, as Hugh says, to put in some fragment of the iteration strategy for M infinity. Okay, so we verified that this is a ground. This was the first step. And for this, we use this theorem of Bukovsky's. Maybe let me write down the rest of the statements, and then maybe I say one word about how you do this. The second thing was that we actually verified that what they had done is they had said, okay, we start out with this model, it satisfies B covering, it's fully iterable. By the way, why is it fully iterable? Oh, anyway. They start out with this model, it's fully iterable. And then they go for the core model in the usual way, that they take hulls of thick classes. It turns out that this is already the core model. So nothing is going to happen on the way from M infinity to the core model. So this is the core model. When I write these things, I always mean that is a ground of M. This is the core model of this model. Okay. So the next thing we showed, I mean, this is also the order, I think, in which you have to prove these statements, that this model up here, so this was the hardest part. This statement really shows that what you are doing is, in reality, analyzing the Hort of a model of a fragment of determinacy, I guess. Namely, we show that this is the Hort, not of M, but of M when we, sorry, when you do the Levy collapse of the strong cardinal of M. So this is the hardest part because I mean you don't really see M in this model. So you try out all different M's, and in the end you show that you don't see M. You cannot define M in here, but you can define the direct limit system after all. Okay, so you get that this is contained in here. This was a bit difficult. Okay, and then actually you show finally that, I mean, this is a ground question. Are there any other grounds? So in the end, you show that this is already the mantle. So there isn't any other ground. So this is the least ground. This is the mantle. And by showing that this is the mantle, this also shows that this is actually a model which doesn't have a non-trivial ground, right? Which is called, I think, a bedrock. Something is a bedrock if it doesn't have a non-trivial ground, if I'm not mistaken. So this model, I mean, it has a Woodin cardinal, okay, fine, but it's not an L of E model. So this blocks the argument, the theorem of Hughes we saw before. You cannot prove that there must be a non-trivial ground. So this is a bedrock. So this is the mantle of this model. So now,
So, Ralf, did you say that was the only ground?
I'm sorry?
Did you say that was the only ground?
No, the smallest. Maybe I said it, but I didn't mean it. So this is the, I don't know. What I meant to say is that, you know, all the, you have this model. There is this canonical recipe, which I didn't really talk about, but what I hinted at gives a canonical recipe for obtaining fine structural grounds. You iterate the least measurable, and then you start making an initial segment generic over a model using P constructions, blah, blah, blah. So this gives a canonical class of grounds. Each of them can see M infinity, okay? So this guy is contained in all these grounds. But it's smaller than all of them. So this is kind of the smallest ground. So this is the intersection of all grounds. It's itself a ground, and it's the mantle. Okay, so the trick how to prove this is that we use this theorem of Bukovsky's. I think if we hadn't known about this theorem, I don't know. So it gives a nice criterion for when something is a forcing extension. The thing is that the only thing is that you have to verify is that you have a strong form of the kappa chain condition for some kappa. So what do I mean by strong form of kappa chain condition? You know, the point is if W is a ground of M, then the forcing will have the kappa CC for some kappa. So what does it mean? This means that you can kind of guess, if you take in the outer model, in M, if you can take any function from any theta, let's say to the ordinals, there is a function in the ground model which kind of guesses the value at each argument, right? And there are by less than kappa many guesses. Okay, so give this property a name. For every function in the extension, there is such a guessing function in the ground model for some kappa. if that's true for your inner model, I mean, if that's true for the pair inner model and the given model, then the inner model is a ground. This is Bukowski's theorem from the, I don't know, 60s or 70s, I forgot. And this is used here. So you use the fact how this model is obtained, and you verify this statement. One last thing I want to mention is that, of course, now you don't want to stop here. Next thing is maybe you look at the least model with a strong cardinal, and it has 2 wooden cardinals. And the surprising thing is, let's forget about the second wooden cardinal. I mean, again, you will have that if you have the least model which has 2 wooden cardinals and a measurable cardinal above, it will have this model as an inner model. And you can use this inner model of that model as a starting point to do this whole analysis. So what you will get is that you will get an M infinity based on this kind of small inner model. It's a too small inner model of a model which is not too small. And it will produce exactly in this fashion the core model, a too small core model. And you have the very same analysis. So this is a situation where you have a model which is not too small. It has 2 wooden cardinals, but it has a too small core model, and you can analyze the mental. And of course, it has nothing to do with 2. You can do it for 3. You can do it for, okay, but this is where things are at the moment. So thank you very much.
Are there any questions for our speaker?
Should.
Yes, Hassan. Yeah.
Yes, there you are.
I don't think there's anyone else. Okay, yeah.
Go ahead.
Oh, Philip, go for it.
Just to, Ralph?
Yes, I'm listening.
Okay. I mean, just to complete the picture, I mean, going down low, you haven't given a lower bound such as like not a pistol for an LV model to have no.
Sorry,
You haven't given I mean, could you state a lower bound, for example, something like not a pistol for an LV model not to have any non-trivial?
you mean for an arbitrary model, forgetting about LOPs, or for LOPs?
Take an LV model, right? But, I mean,
If you are below a wooden cardinal.
so anything below a wooden cardinal.
If the model doesn't have a clear model with a wooden cardinal, if LOP doesn't have a clear model with a wooden cardinal, then I think I stated it in the very beginning.
Sorry, I was
Yeah, don't worry.
Okay. Can you state this again?
Yes, I can do that. Suppose for all functions f from any, let's say from an ordinal to the ordinals, okay, where f is an n, there is
So it exists for the cardinal.
yes.
Exists the cardinal.
Suppose there is some kappa such that for all such functions there is a guessing function, f is an m, a guessing function, you know, it goes to sets of ordinals, this one is notation g in W such that for all I less than theta, I mean the value of f at I is guessed, and g of I is size less than kappa, then m is a forcing extension of W via a kappa CC forcing.
Can you give the word about the forcing that you use about the...
I have no idea which forcing he used originally. I know a write-up where the forcing looks like the Slender algebra.
No, it's not too difficult.
I'm sorry?
It's not too difficult. There is a similar, I think it's true for Penka, a similar characterization and this characterizes when the forcing is capital C, and there is something that characterizes the case where the forcing is of size is capital.
subset of ordinals, you can find a family of less than kappa subset of that ordinal. Such a huge set is union of the subfamily.
But do you know if you originally used, or if they originally used infinitary images, or?
No.
I mean, the proof I know is infinitary images.
Before we end, Asaf,